When you think of chemistry, do you just picture a bunch of super complicated formulas? Well, forget all that. Today, we're going to look at it a different way. Think of chemistry as a detective's toolkit, a set of really powerful methods for investigating the world all around us and, yeah, solving the mysteries of matter. Let's jump right in.
All right, so look at this. We've got two piles of white crystals that look pretty much identical. One's salt, one's sugar. Now, without tasting them, and you definitely don't want to do that, that's rule number one in any lab, right? How could you possibly know which is which? This is exactly the kind of mystery a chemical detective has to solve.
And that is what chemistry is really all about. It's the science that gives us the answer. It's how we investigate all the evidence and ID the culprits. Seriously, think of it like dusting for fingerprints, but we're doing it at the molecular level. So go ahead and grab your magnifying glass. It's time to open up our toolkit.
Okay, tool number one. Imagine you've just arrived at a messy crime scene. What's the very first thing you do? Well, you've got to separate the evidence. You have to figure out what's important and isolate it from all the background noise.
Let's be real. The world is messy. Things are rarely pure and simple. That rock you picked up, a glass of seawater, even the air we're breathing right now, they're all mixtures, just a jumble of different substances all mixed together. So a chemist's first job is to carefully pick that jumble apart to see what's really in there.
So how do we actually do that? Let's walk through this classic example, a mixture of iron filings, salt, and sand. First up, as you see in step 1, we can just use a magnet. Easy. It'll pull all the iron right out. Then, for step 2, we add some water. The salt dissolves, but the sand doesn't. Now they're separated. Next, in step 3, we pour that whole mixture through a filter, which catches the sand. And finally, for step 4, we just gently heat the salt water. The water evaporates, and what are we left with? Pure salt crystals. See? Each piece of evidence is now isolated.
And here's a great look at that third step we were just talking about. Filtration is a classic detective move. It's a really simple physical technique that lets us trap a solid that won't dissolve. In our case, the sand, while the liquid just passes right on through. Just like that, we've separated another piece of the puzzle.
Okay, so we've isolated a substance. We've got our evidence in a bag. But now, what is it? How do we get a positive ID? For that, we need our second tool, the ability to find its one-of-a-kind chemical fingerprint.
Every single pure substance has its own, well, you could think of it like a rap sheet, or even better, a unique chemical fingerprint. It's a set of properties like melting point, boiling point, and density. And here's the key. Those properties don't lie. They're always the same for that substance, making them an undeniable identifier. Let's zero in on one of the most useful fingerprints out there, density. It sounds technical, but it's really just a measure of how much stuff, that's the mass, is crammed into a certain amount of space or volume. If you know those two things, you can calculate its density, and that is a key piece of its identity.
Okay, but how does this actually help us in the real world? Let's try a little pop quiz. You've got 2 cans of soda, regular and diet. They look exactly the same, but I'm telling you, one of them will sink in water and the other one will float. So which one is which, and more importantly, why?
And the answer is that Diet Coke floats. Kind of weird, right? But here's why. The regular Coke is loaded with a lot of pretty dense sugar. That makes the whole can's density just a little bit greater than water's, so it sinks. The Diet Coke, though, uses just a tiny pinch of a much less dense artificial sweetener. That makes its overall density just a bit less than water, so it floats. A tiny difference in the recipe totally changes its physical fingerprint.
And this same exact idea helps us solve all kinds of other puzzles. Take pennies, for instance. If you were to measure their density, you'd find that pennies made after 1982 are actually a lot less dense than the older ones. Why? Well, it's a clue that something must have changed. And it did. The US Mint switched the recipe from mostly copper to mostly zinc, which is a less dense metal. The fingerprint changed, and that tells us the story.
All right, so we know how to separate things and how to identify them, but what about when stuff actually changes? When chemical reactions happen. For that, we need our third and maybe our most fundamental tool, a law that you just can't break.
And here it is, the big one, the law of conservation of matter. All it really says is you can't create matter out of thin air, and you can't make it just disappear. When you burn a log in a fire, it might look like it's vanishing, but it's not. It's just changing into ash and smoke and gases. All the original stuff is still there, just in a new form. And the person we have to thank for this incredible discovery is a brilliant French chemist from the 18th century named Antoine Lavoisier. He conducted these incredibly precise and careful experiments, weighing everything before and after a reaction, and he was the one who proved that no matter what you do, the total mass always stays the same.
This is such a great way to picture how this law works. Imagine you have a pile of paper clips and a pile of washers. You weigh them separately. Then you link them all together, making these little molecules. Well, if you weigh that final product, its mass is going to be exactly the same as the weight of the individual parts you started with. Nothing was created, nothing was destroyed, it was just rearranged.
But here's where the story takes a really tragic and ironic turn. Lavoisier, the very man who proved that matter is always conserved, was living during the French Revolution. And because he had also worked as a tax collector, he was arrested and ultimately executed by guillotine. As the story goes, one official chillingly remarked, "The Republic has no need of scientists." A terrible, terrible loss, but his unbreakable law lives on.
So there you have it. We've separated our evidence, we've found the fingerprints, and we've learned the unbreakable law of the land. Let's pull this all together, shall we?
So here it is, your chemical detective's toolkit, all laid out. Tool number 1, deconstruct mixtures. Use their physical properties to pull them apart. Tool number 2, find the fingerprint. Identify those pure substances by measuring their unique properties, like density. And tool number 3, obey the law. Always remember that matter is conserved.
And you know what? That's the real secret of chemistry. It's not about memorizing a million different facts or having access to some fancy lab. It's about understanding a few powerful, fundamental rules that explain how the entire material world works. It's really just a way of thinking.
So now you have the toolkit. You have the basic tools of a chemical detective. You know how to look at the world, how to start taking it apart, and how to figure out what it's really made of. So the only question left is, what mysteries are you going to solve first?